Hi everyone, I'm Luis. This is joint work with Leo Wanner and Stephen Schockaert. We're from Cardiff Uni and Pompeu Fabra University. And collocation classification with unsupervised relation vectors. I'll start the talk with giving a little bit of background on collocations and also word and especially relation embeddings. Describe a bit the experiment that we did, a little bit of analysis, and finally some conclusions and open directions for future work. So a couple weeks ago, there was this tweet that went viral, and I'm going to read it for you. It says, in Spanish, attention is something you lend because you kind of want it back. In French, you make it because it's not there if you don't. In English, you pay it because it's valuable. And in German, you gift it because it's really a present. I wish I knew all languages. And other people replied to that thread with examples from other languages. I learned that in Chinese, you focus attention because it can be dispersed everywhere, that in Japanese, it's attaching one spirit, or that in Hebrew, attention is putting your heart in something. Regardless of the correctness of all these contributions, these people perhaps unknowingly were discussing the phenomenon of collocations. These are, according to Kilgarif, restricted lexical co-occurrences of two syntactically bound lexical items, and we'll flesh this out a little bit later. The recovery from corpora is important for two main applications. One, for improving language learning resources, and for what is relevant in our setting, also for downstream NLP, especially generation, machine translation, paraphrasing, and simplification. But it has also been argued that simply collecting lists of words that frequently co-occur is not enough. For a language learner, understanding really the semantic difference between coming to fruition and bring to fruition, or have an approach versus take an approach, is not straightforward. So in this paper, we propose the task of the semantic categorization of collocations. So the input is a pair of words, which we know they are a collocation according to a certain linguistic or statistical criterion. And we want to predict the semantic category, the lexical function, according to the meaning text theory of that collocation. The notion of collocation has a strong statistical tradition with pairwise association metrics like PMI or any statistical test, but there is a complementary line of thought that considers a more lexicographic approach to the modeling of collocations. These are formed by a base, which is a freely chosen word, like for example advice, and it's collocate, whose choice depends on the base, for example follow. So here we present experiments on dataset manually collected by Igor Melchuk, who is one of the main personalities behind the developments of the meaning text theory, and 8 lexical functions. As you can see, they refer to intensity, for example, strong accent, or carrying out, or the notion of participating, for example, engaging in an activity. The data set is, the experiments we run is on nearly 5,000 collocations, and here you have the statistics of this data set. And as I said, the features are the word embeddings of the base and the collocate, and certain composition, addition, difference, concatenation, and multiplication. And regardless of the composition of those embeddings, we also concatenate their corresponding unsupervised relation vector. Now, where do these relation vectors, these points in space for pairs of words, come from? So we use the model that we presented last year in calling, and I'm just going to give a quick overview on this. So assuming we want to learn a vector for the words A and B, we take all the sentences where A and B co-occur, and we take simply the average of the words occurring before A, the words between A and B from some pre-trained embedding model, and the words occurring after B. So now we have, for that particular sentence, if we have a 300-dimensional space, we have a 900-dimensional space that tells you that tells us a little bit about the distribution of that pair of words. And we do that also for the cases where, for the sentences where these words occur in a flipped, so B occurs before A. And then we average over all the sentences where this happens. So we average all the left contexts that occur before A, the left contexts that occur before B, and the same for the middle and the right contexts. And in the end, again, if we have a 300-dimensional space, we have an 1800-dimensional relation vector for them. And then I'm not going into details for lack of time, but 1800 dimensions is sometimes untractable, and it has also some properties that, depending on the application, we may not want them. So we reduce their dimensionality with a conditional autoencoder to 300 dimensions again. And that's it. So we run experiments on this manually compiled data set on collocations, and we compare how we do with the DiffVec data set, which is a well-known collection of relations for the task of relation classification. And we have several semantic relations that range from hypernymy, event, collective meronymy, collective nouns, meronymy, and so on. So if you're not too familiar with it, it comes with WordNet relations or relations from the blessed data set as well. So we train a linear SVM with glove pre-trained embeddings, word and relation embeddings. And again, what we wanted to see is whether there's a big difference or a major difference in performance, and how difficult are collocations to classify as opposed to other more established relations. So the results were that on word embeddings alone, the concatenation actually works quite well, and that the best model is that one where there's explicit relational information being encoded there, so not the auto-encoded one, but actually the longer, although the difference is small. But I guess the most interesting conclusion is that the semantic categorization of collocations is difficult, and there's roughly about between 10–15% of drop of performance of any model when compared from the experiments on DiffVec versus this collocations collection. Very quickly, so a couple of examples of when the vector difference model that doesn't do very well as opposed to the inclusion of the relation vectors. So the lexical function oper is, as I said, denotes the notion of performance, and the real is like the realization of something. An example of oper could be bear affection, and of real do drugs or observe a convention. And it's typical that in these lexical functions, they are typically being used with light verb construction. These are typically light verb constructions. So the embeddings alone tend to not be very well defined because of the inherently ambiguity of these verbs. So there we found that we obtained a nice increase in the performance. And another interesting case was the magnifier lexical function. So for example, strong backing or tired cliché versus the bond lexical function, which kind of denotes not really magnifying, but rather a very positive connotation, like a sweet deal or a magical solution. And here, this was another case where the difference in performance was pretty large. And yeah, that's more or less it. So we kind of conclude that collocations are a challenge for embedding-based models. It's natural in the sense that these are sometimes arbitrary, semi-frozen multi-word expressions, so they are not really as frozen as idioms, for example. And as you saw at the beginning, they are highly language dependent, but signal from relational word vectors, from relation vectors helps. And for the future, shortly, we would like to look at other relational models or explore contextualized representations, maybe going sense level and multilingual, and expanding the scope of our work. So you've got the models and the data and code for this paper and the data set as well on the slide. Thank you.